Hello everyone, welcome back to the afternoon session of the workshop. In the afternoon, we have a crypto session, which has two really interesting talks, followed by a really fascinating keynote by Dr. Amir Houmansadr. So the first talk in the crypto session is about decoupling permission management from cryptography for privacy preserving system by Ruben.
Hallo, I'm Ruben from VUB, Vrije Universiteit Brussel in Brussels, Belgium. And my work is on privacy enhancing technologies and specifically on the usability of privacy enhancing technologies. And my main thesis is basically this: designing privacy enhancing technologies or implementing them is kind of hard, right? You need to study cryptography and understand a lot of cryptography before you can actually do something with it. And as an example, or to set the scene, I would like to have a look at the private group system in Signal. So historically, originally, the group chat system in Signal was rather simple. So this is my family chat. So my mom, Alice, my dad, Bob, and my brother, Charlie. And they wanted to add me to the group chat, and what happened in Signal before was, well, Alice would send a message to Bob and to Charlie and to me saying, hey, this new member joins the group. And it would just be sent via the Signal protocol, just end-to-end encrypted. And then all the group members get an update to the group state. They all know, okay, now we have 4 members instead of 3 members. That comes with an issue, right? Because in Signal, you don't assume that every message always gets delivered. You may miss messages, so you have a consistency issue. Some people might have a different view on the group state than other people. And so in 2020, Signal introduced an update to the group system. They, as of 2020, they store the group state on the server. But that also comes with an issue. If you store the group state on the server, then the server knows who is in the group, right? So they invented a private group system. They designed a private group system consisting of an anonymous credential system, a few zero-knowledge proofs here and there, such that the group state can be encrypted on the server. So the group state actually is a list of UUIDs, so the identifiers of the users, encrypted, such that the server does not know who is whom, and it's a list of those identifiers. That's what's happening. In this case, if Alice wants to add me to the group, then she would first contact the server, say, hey, I want to update the state of this group. She would use an anonymous credential system to authenticate. So she says, I'm one of the admins of the group, without disclosing which admin she is. Well, disclosing which anonymous admin she is. And then Victor would allow the change of the group state on the server, and then the other members can either download the new group state or get it gossiped by Alice. So Alice would still send a peer-to-peer kind of message to all the group members with this update. Now this comes with a few advantages and disadvantages. So Signal actually wanted this for like the consistency, but also because they wanted to introduce a whole lot of new features to the group system. For instance, they wanted to support a difference, like a distinction between admins and regular members. Admins can update the name, the description, the member list of the group. While members can't, they just can send messages. And they also wanted an invite system. So you can nowadays have a link and then distribute the link to people, and then people can join the group. Or you can send an invite to a person, and then this person is not in the group, but also not outside. They can accept the invitation and then promote themselves to a member. So they wanted to introduce a whole new set of features. And with this new group system, with the group v2 system, they also introduced, well, they fixed the consistency issue. And the privacy of the group members is still kind of guaranteed by this anonymous credential system, right? Now, it's not perfect. For instance, the role field whether you're an admin, an invitee, or a member, is not encrypted. So the server has access to the count of admins and members. So it's not perfect there. And the server still has to store the state. It is encrypted, but depending on the size of the state, they can still infer the number of members, the number of admins, all those things. Another drawback, well, it's a very beautiful cryptographic construction, of course, but it's still a custom cryptographic construction. They had to put effort in that to design it and so forth. And something that triggered my interest is that if they want to update this system, if they want to introduce new features, they have to think about the cryptographic aspects. Like if you want to add new features to this system, you want this in a privacy-preserving manner, which means change the cryptography behind it, or adapt it at least to keep the privacy-preserving features. And so that's what piqued my interest. So that's what I'm going to focus on this presentation. And the concept here is I want to design a system where the permission system that we're looking at here is conceptually independent of the underlying cryptography. So the permission system in the signal example is tightly coupled to the cryptographic implementation. Cryptography and the permissions goes hand in hand, and I want to design a system where this is decoupled. And so let's have a look at how you can do this for Signal. And to get to the point, let's model the permission system for Signal in Datalog. Datalog is a fragment of Prolog, a subset of Prolog, and Prolog is a logic programming language, right? And the nice thing about Datalog is it's extremely simple, both in terms of readability, but also in terms of implementation. If you want to implement something, a Prolog engine, a Datalog engine, excuse me, it's something rather simple. It's also not Turing complete. It's something very compact. You can write a Datalog engine on probably 20 lines of code, right? So what does this all mean? So these are rules, right? So these are the rules of the system. So if you so a member in the new group is someone who is either added to the new group or someone who was already in the group from before. That's the first two rules there. And so first rule says if someone, and the someone is called member, it's a variable over there. If the someone has added some other person to the group, then you're part of the new group. That's the first rule. The second rule says you're still in the new group if you have not been deleted by someone. So this way, this is only a fragment of what if you want to implement a whole system for Signal, you will need a few more rules, but this is a way to model what Signal is doing for the group system, right? You still have to add invitations and name changes for the group and description changes and all those things, but this is basically how you can model it. And then the last rule basically says you can only carry out an action if you have been granted permission to do this action, right? So in other words, you are violating the rules of the system if you're carrying out an action and you are not allowed to carry out the action. That's the final rule over there. So this is a way to model the Signal group permission system. And if you, to use this, you could evaluate this rule set against the group state. For instance, this is the old group state, so we have Alice in the previous group, the group that's currently stored on the server, and she is a member, and then Bob is also a member in this group. And then you declare the action that you want to carry out. We add Carol, we give her the member role, and Alice is the person that adds Carol to the group. Okay, so we now modeled all those things in Datalog. What are we going to do with this? Well, we can use a data log engine to query what the logical consequences are here. And so you can prove that Alice is a member of the new group, you can prove that Bob is a member of the new group, you can prove that Carol is a member of the new group, and you can do this in just standard Prolog or data log. This will just work. If you execute those queries, then Prolog will tell you, yes, that's correct, because of the rule set that you define. And well, you prove that no rights have been violated, and you prove that at least one more admin remains in the group. That's something a normal data log or Prolog engine would be able to tell you, right? And it turns out that if you look at data log and you try to model this into a zero knowledge proof system, you can actually make this very efficient. And that's something that we did in 2022. We designed a data log engine that can work with these kind of programs and with this kind of data, and process the program into a zero knowledge proof, and transform all these group states to assertions in the system, and then make a zero knowledge proof that actually these queries are correct. There were some limitations in 2020 that we are still working on. There are a few that have been resolved meanwhile. But it turns out that this is very efficient to do in zero knowledge because of the structure of the data log programming language. A few notes. So I say, turns out it's very efficient. So if you compare this thing we called circuitry with imperative systems, there are zero knowledge proof systems that are just based on like Turing machines, Turing complete languages. It's perfectly doable these days to take a Turing complete language and make a zero knowledge proof out of it. It turns out that when you use something like data log, you can use a pre-processing step to make this proof very efficient. So that's the interesting aspect here, and it's very suitable for permission systems, as I showed there. Since 2022, so if you read the paper that we published back then, the performance was not very interesting. But meanwhile, we found out how to make this efficient with this pre-processing step and then ordering all the assertions in certain ways. So there have been a lot of performance improvements that we didn't publish yet, but that's coming along. Then one of the details that we usually leave to the imagination, you could say, is how to interface with the secret group state, because we still, so these facts like the group structure, it has to come from somewhere. You have to certify that this is correct data, and only then the circuitry system can actually act on it, right? How do you do that? These steps are still, well, you could say not modular, right? So you still have to manually encode or code a zero knowledge proof in order to get them into circuitry. These are also things that we're working on, a custom certificate system or adapting it. I would really like to make something for Signal specifically, get the current Signal group state like it currently exists, and then transform it into something that we can work with here. Something I'd really like to do. And then another idea there is, well, currently the role field, for instance, it's not encrypted for Signal, but we could, with a system like this, actually also encrypt it and use it as data in the data log system, which would improve the privacy over what Signal currently has. So that's something I'd really like to try out. Additionally, you don't even need the group state to be encrypted anymore, because you don't need access, the server does not need access to the group state. It only needs to be sure that the change is correct, so we could get away with just storing a commitment on the server. And if you use a vector commitment, the server doesn't even know how big the group state would be. So that's an additional advantage you could have there. And then circuitry lacks a few features to actually implement this, features that we are working on. It's been a very tough debate with my colleague on whether or not we can efficiently implement them. I believe we can, so that's why I'm presenting, I suppose. But especially for negation, so you have to prove that no rights have been violated, which means that you have to exhaustively search the data log state space, basically, and prove that there is no such assertion such that the rights have been violated, right? The debate is this possible to do as efficiently as the rest of circuitry currently is? So that's one thing. And the second thing is we have to be able to implement open queries, because you have to prove that the new group state that you supply to the server is complete. You list all the members. It's not enough to prove that all the members you list are actual members of the group. You have to prove that you listed all of the members. So that's also an open question on how to correctly implement this. But I think we both agree there that that's actually possible. So the question is just how efficient would it be? Now, what is the advantage of this approach over the one of Signal? So just to reiterate, if you read the paper of Signal, it's well written, it's a good design, but you need to study the cryptography, understand the cryptography. It's difficult to audit for someone external if you don't know the cryptography. If you look at a system like circuitry, you can validate the underlying data log system independently of the permission system that you build on top, which means it's easier for non-experts to build a permission system in zero knowledge without actually really needing to understand a lot of the cryptographic details. So it's easier to audit, it's easier to modify, it's easier to make something yourself, to play with it even. And I think this is like a general thing that maybe the community can focus on, like make building blocks in such a way that more people can use them and that they can get a wider audience. So also in general, if you have a layered, a modular, a decoupled software engineering approach, it's considered a good engineering practice to make individual building blocks, and that can really work together and be independently audited and edited. I went over that one. So remaining questions for this is, what's the real world performance? That's one thing. One thing that I would want to look at on the short term with regard to the Signal example. And how do you integrate this into Signal? Let's say this actually works and it's efficient. Can we actually get this into Signal itself and make a demo out of it? How do you do that? Will it all fit? And also, what's the real impact on security? What's the model here? It's not very clear what's going on there, but that's also something we need to study. So I think that's my presentation.
Let's thank the speaker. Any questions in the audience? Then I have a question. Do you foresee any application scenarios for this work other than group in Signal? So for example, it could be something like, do you see applications in, for example, searchable encryption or those kind of scenarios?
So searchable encryption would be an application even outside of zero knowledge, I would say, right? Datalog is Datalog is the underlying language for instance, SQL. SQL is modeled on the same principles. So yes, I would say that something like Datalog would be interesting in the realm of searchable encryption, because it also has a mapping on how to search databases. But specifically for the zero knowledge part, the original idea that we had was around COVID. We had all those EU digital COVID certificates in Europe, and they just listed all your medical details. That's a lot of fun. The application that we got from the government just was green or red, but the QR code itself contained your medical record. And so what we wanted to design was a system that could ingest the original QR code and then spit out another one in zero knowledge. And the policy the policy that you need for the QR code was different based on the country where you were, the reason that you were scanning the QR code. So for instance, in a bar, you just needed one vaccination, and then if you wanted to go on an airport, then you needed two, and all those kind of policies. And it would be really neat to just encode all those different policies in data log, base yourself on the same kind of data, but then you can just on the fly prove whatever you wanted and whatever you needed. So that was the original motivation for circuitry, basically.
Okay, and a follow-up question, then if we want to actually use this in a different application scenario, then what kind of research or what kind of work would be needed to actually translate the current work?
The main roadblock is really this input, like the certificate input. For instance, in the case of the COVID certificate, read the QR code, get it into circuitry, and from there on, it's all done, it exists, right? So that's the only thing that really needs customization, and customization for basically every single application. That's the major roadblock. Other than that, it's quite straightforward, I would say.
Okay.
Did you have the chance to look at the MLS of the IETF? And if so, is that also similar to what Signal does?
I think MLS is mostly focused on the end-to-end encryption protocol part, right? Yeah, but I think the management of the group state is out of scope. I'm not sure. I'm not sure. I'm not sure. As far as I understand, it's just for the end-to-end encryption part.
Maybe I'm wrong, but I thought the reason why there was like such a huge effort in working on the MLS is because the group messaging in Signal doesn't scale, so they needed to.
Yeah, but the scaling in the group messaging for Signal is mainly because because they do client-side fan-out of messages.
Yeah.
And MLS is like a group key management solution, but it's really specifically for the end-to-end encryption part.
I see.
Yeah.
Any other questions? Let's thank the speaker again. Next talk is on query privacy in data spaces by George Palios.
Okay, great. So good afternoon. I'm George Polizos. I'm now in many places at the same time. I'm at the Chinese University of Hong Kong, Shenzhen, where this research and effort has been made and will continue. And I'm also with a spin-off, Greek spin-off from my previous lab that's called Exceed, where we have worked on data spaces in previous projects and was essentially the starting point for this. No, this is the wrong doc, sorry. Okay, so what I said still applies. So this is work with Xuan Liu. And we are at the School of Data Science at the Chinese University of Hong Kong. So I'm not a cryptographer. And in the last few years, I have been using cryptography for applications. But my background is in networking, and I have been slowly going up the layers. And for many years now, I'm interested in data-centric solutions. So being now at the School of Data Science, and data spaces try to bring value out of data and in a controlled way. So I'll talk a little bit about data spaces and fireware or figware, which might be maybe with the motivation of this talk the most interesting part of it, then about system design, and a little bit about performance and security evaluation. So I don't know if you're aware, but data spaces have been around for a while. As motivation now, there are globally networked production processes, and they demand data exchange that goes through company and sector boundaries. And therefore, in that context, data security, data sovereignty are really critical. On the other hand, the idea is that up to now, everybody protects their data and nobody can use anybody else's data. So we are trying to make, and data spaces are trying to make this, to improve this. And therefore, the idea is to have secure, controlled data sharing environments with data sovereignty, interoperability, which is not trivial, developing domain-specific ontologies so that you know what to look for, what to ask for, what to understand if you get something. Trust at various levels, governance, and also incentives for collaboration, including perhaps monetization of data. And there has been an International Data Spaces Association, I'll show you a slide later about this, that has developed the concepts and standards around it. It's backed by the EU for a number of years now, but there is recent interest also in China. And there is alignment with GDPR, the Chinese version of it, people, and there are data spaces that do exist. Here are some, I'll show you more. And there is a standard for a security gateway that is at the center of many of those exchanges. And both GAIA-X and I guess this origination of the standard have some German roots. So here, a list of data spaces I could get these days, the names. The interesting thing is they are across domains, all over the place. I really don't know exactly how active they are, exactly what's going on, but my understanding is that it's beyond research and development, and it's at least at the beginning of real operation. And as I said, the European Commission is pushing for making data spaces work. And the idea is to provide good quality information in a trusted way for all kinds of things. For example, supply chains, for example, for the food supply chain, and many other applications. So I think this is an interesting domain. Okay, so okay, I skipped the IDSA, the International Data Space Association slide. It's not important, but this is a standard from the Data Space International Data Space Association, IDS or IDSA. And it shows schematically what data spaces are about. So there are data owners, data users. A key entity is an IDS connector. So essentially, it's a gateway, it's a translation agent, it helps with interoperability, it helps with access control. Okay, and then there are a number of entities and services around it. So there are brokers that help you figure out who has what data. There are identity providers. There is vocabulary, okay, and these are per data space. So data spaces are different. Maybe the general form is the same, but then the specifics depend on the application domain. So we'll try to see what happens here. The idea is that the data owner keeps the data at least at the level of connector, either behind the connector or on the connector, but the connector could be also owned by a third party, okay? Or there could be an additional connector owned by a third party. So there are various architectural solutions for that. So there are metadata privacy questions here, okay? So not only the data themselves need to be protected, but what you are looking for could or should be protected, okay? When you do that, and all such questions, okay? And this is where we started working on, okay? So essentially, mostly the queries parameters, the query patterns, okay, we tried to protect. And we are using a number of tools, like standard tools from cryptography and privacy enhancing technologies, searchable encryption, obfuscation, ephemeral credentials, to get better end-to-end privacy, including metadata privacy. And let me describe a scenario, a motivating example, which I think is interesting and useful, and we can discuss further. So let's say we have an energy data space, okay? There are two energy resellers, S1 and S2. They have their consumption data, for example, how much energy they have sold last year, okay, or in the past years. And there is an energy supplier, P1, that is interested to get some of these data. Now, the resellers don't want to reveal their data, okay? The reason is they don't want to show their market share, things like that, okay? On the other hand, they have an incentive for the energy supplier to figure out what to do. For example, the energy supplier might want to extrapolate, predict energy demand in the future in order to make investments in energy. So, for example, he wants to ask for consumption during, let's say, year 2024 in order to prepare for year 2026, okay? So to some extent, S1 and S2 are in the same boat, but they still don't want to just reveal their data, okay? So in my imagination, in my view, this is the real good scenario for data spaces. So everybody keeps some level of privacy for the data, but they allow the data to be used. So we can have those at the ends of a data space, and we try to see, how we can make this happen. So somehow S1 and S2 will be willing to somehow provide encrypted forms of their consumptions during that year. If somehow P1 can get the sum, doesn't care about the details, who has consumption 1 and 2, okay? So in the middle, we can have different solutions. So we're using searchable encryption that doesn't really solve this problem, okay, but solves simpler versions of this problem. We could do homomorphic encryption, actually just additive homomorphic encryption that was mentioned earlier today would resolve this problem, or multi-party computation. And we're looking into these directions for future work. Okay, but actually, what we do is also try to look at security not only through cryptography, but through architectural solutions, incentives, who is allowed to do what, legal enforcement of things, etc. So rather than having a cloud in between and not specifying what's happening and having a fully decentralized system, our current solution is based on a proxy, on a centralized solution that is based on the connector that I showed you before. One of those connectors becomes the important party in this computation and can simplify matters with various assumptions about what they can do, what they can learn, and what information they can provide to whom. Okay, so this is the current version of what we are doing. Okay. So in order to avoid revealing C1 and C2 even to the proxy, we're using searchable encryption. In order to avoid P1 to really say what they are looking for, we do metadata obfuscation, okay, hiding query terms, queries, and things like that. We don't do onion routing, but if needed, we could do things like that. Now, right now, things the way they are, essentially, we need the parties to use the same key in order to operate this cryptography. So, for example, secure computation without decryption, we don't do it. Okay, but as I said, we can go towards multi-party computation and go over that. But we also do some other things. That is, we use standard software and modern identification techniques in order to ensure scalability, compliance, and extensibility. Okay, so we use Figware, which is a standard open source set of software that helps in this domain. And we use decentralized identifiers and verifiable credentials in order to have ephemeral IDs that provide a lot of privacy. So, Freeware is a set of open source software that is supported by the Freeware Foundation in Europe. Among other things, it has a context broker for data spaces, that is this NGISI LD. And also data space connectors, and can do identity management based on OAuth and X509 identities. So we extended a proxy server to add searchable encryption, DIDs, verifiable credentials, and obfuscation to provide some of the metadata privacy features. Okay, I will not stay too long about this. One of the reasons that we use searchable symmetric encryption is that it's relatively easy both to comprehend, and it's available already in various databases, including MongoDB. And it has good properties, can have keyword search, it can do linear or sublinear search with keywords, and we can encrypt the queries, and so if we don't have to do operations, then the server, the proxy server doesn't find out anything about the content of the queries or the content themselves. And we were based on these two papers down there for the version of searchable encryption we have done. In addition, we do metadata obfuscation. So we do IP hashing, add some noise to timestamps, some padding, okay, and therefore we do more or less standard things to avoid linkage. And then we also use, as I mentioned, DIDs and verifiable credentials. And the idea is that every query gets its own decentralized identifier. If you haven't, if you're not aware of those are identities that essentially you can self-provide. Essentially, it's can be something like a public key, but it has more features because it has an indirection. There is a DID document, and you can circle around identifiers. And if you need somebody to really authorize you to do things, then we use verifiable credentials. So somebody signs that the ID you provide with the authorizations you have. And so we use this as a way to provide both privacy and strong security guarantees. So only legitimate requests with correct ephemeral credentials succeed through the system, and they don't leave many pointers of who did what. We did some security evaluation through formal analysis. I don't think it's very important to go through this right now. Looked at various components we have, and essentially argue that they perform as we designed them. There is a system working, minimal system, so there could be some attacks that have been performed. Again, I'm saying this is a very preliminary work, so I don't think this is very important. I don't know what, so average latency is in tens of milliseconds right now, but it's a very small system. I don't know if this means much, but it's on the way to feasible implementations. Data spaces are not expected to be, maybe they are, but they are user level. So even seconds would be okay to have response times, etc. So I think this is not a major problem. So conclusion, so essentially we set up the problem of privacy-preserving queries and metadata privacy in data spaces. We proposed as a first step to use searchable encryption. We integrated this to a data space, to a minimum data space environment, added obfuscation and digital identity, modern digital identity solutions. And all of this also is, meets GDPR requirements. We used 5-ware data space software for the integration, so many of the components are standards provided, so makes this both easy to do, to integrate, to implement, but also more and more standard, so that this can be repeated and extended. So up to now, the first results show promise no major problems. The major issue is more requirement analysis. That is, what really we want to get out of data spaces and how much privacy is needed, including metadata privacy. So for example, do we need to do computations over really many entities, many independent entities? So would really multi-party computation be needed, and would that be a bottleneck? So we're going to look at that, also try more advanced query capabilities, look more about regulatory compliance, and also, consider scalability, which is not first priority right now. So it's a start. We plan to work on that in the near future in China, but they are looking also towards Europe, and international trade is important. And data for supply chains are important, and interoperability at really international level is important, and at least in that axis, it seems to be understood right now. So, thank you. I'll stop here.
Let's thank the speaker. Any questions from the audience?
So one technical question. There is in the slides, I don't remember the number, but you said we provide, we hide the sender identity, but without using onion routings. But I didn't understand that.
Could you please repeat?
You said in your solution you provide, you hide the identity of the sender, but yeah, in this one, yeah, yeah, hides query terms and sender identity. So I didn't understand. How do you hide the sender identity?
So, hashing and padding.
So that's
so random hashing. So not very strong. I agree. We can do better in the future.
Okay. And besides,
So for example, one thing we didn't do, we knew how to do it, is onion routing. So try to avoid direct contact. But you don't know exactly. I mean, identities in data spaces might be known and limited. So we have to think about all this thing. It's not the whole internet.
that's also my follow-up question is, you did mention one of the reasons that we having privacy for data spaces is important for market, right? Is there other reasons besides the market? Does it intertwine with security as well? Like do you prevent certain attacks by having privacy?
I don't really know. But of course, security, I think, is even more important than privacy in this context. But privacy is also important.
Oftentimes when we have privacy, there is certain attacks for security that we prevent them, right?
Right.
But I didn't understand in this context, when would that be?
I'm not ready to answer this question,
Okay.
but I'll take it
Okay.
as further topic for thinking about.
Okay, thanks so much.
Actually, I have a question about the security analysis. Could you go to that slide if you can? Yes. It seems like the analysis or how you're showing it's about specific attacks. Like, are you planning to do an overall system analysis for like security for the system, overall system? Like, how are you planning to analyze the security of the overall system, or are you planning to analyze attack by attack?
I'm not sure. Right now, it's case by case, okay? But definitely would like to have something more general. But let's see what is at the core of our solution. So whether it's searchable encryption or something else. If it's something else, maybe it will be much more stronger, and maybe even the identities will be different. And therefore, we might address many of the issues in one thing, but in something that might be less efficient and more difficult to prove. So I take the question, you're right. I don't know how to answer it.
Yes, I am asking this question because actually, generally, this is a difficult problem when you have so many components in the system.
Exactly. Yes.
And that's why I was curious about this part.
Right. So the thing is, as I said, I'm not a cryptographer, and I'm not looking for, the beautiful proof. We are trying to set up a system that is useful, and we might take shortcuts. So for example, one of the issues is that you can allow the third party to see things. And then legislation says that they cannot reveal it. And if they reveal it, you go to court. And in some instances, this is good enough for industry. Okay, so we are still looking for the right level. Of course, we would prefer if it's technically feasible and no information is revealed. Okay, but in some cases, You take shortcuts, and data spaces really have this full spectrum, going from fully technical all the way to legal, okay? So we try to see where it makes sense to stop.
Thank you. Any other questions? Let's thank the speaker again.
Thank you.
Hello, everyone. We have reached the last part of our workshop, and I want to welcome Professor Amir Houmansadr, who is here to talk about fighting internet censorship. He is one of the leading researchers in the area of censorship and censorship circumvent systems. I personally am a big fan of his works, and he does not only work on censorship, he also looks at security and privacy of network and AI systems. In his research career, he has received multiple awards, which includes IEEE S&P Best Paper Award, Google Faculty Research Award, NSF Career Award, DARPA Young Faculty Award, and the list goes on. So without further waiting, I'll leave it to him. The stage is all yours.
Okay, thank you so much. Thank you so much for the introduction. I think I'll get a little bit closer. Yeah, it's an honor to be talking at the Impact Workshop, and I'll be talking about some of the work that my colleagues and I have been doing on the topic of internet censorship. So the internet plays a crucial role in upholding human rights, democracy, and social justice across the world by providing a platform for free speech, access to information, and the organization of movements. Unfortunately, many nation states interfere with how their citizens use the internet, and this is a phenomenon which is commonly referred to as internet censorship. So here's kind of my more formal definition of censorship. So internet censorship is an attempt by nation states to, first of all, regulate what can be done on the internet. Second, monitor how people use the internet. And then finally, restrict what users can access on the internet. And this is all with the goal of disrupting and reducing internet freedom. And therefore, there's a community who works on this topic called Censorship Circumvention, and their goal is to help censored users by making internet accessible and usable everywhere by winning some technical games against the censors. So what am I doing at the Metadata Privacy Workshop? And what's the connection? So if you look at the definition that I provided for internet censorship, you can see this is about detecting metadata, and this is about metadata privacy, right? So like for the censors to be able to censor, they need to identify metadata about users' traffic, and they need to do so without interfering with other traffic. And therefore, I feel like this topic of censorship resistance fits well in the context of metadata privacy. And in fact, you'll see that a lot of the work on internet censorship appears at venues around privacy enhancing technologies and privacy and things like that. Okay, so I'm here for a reason. But why do I work on this topic? And I have 3 reasons to tell you why I enjoy working on the topic of censorship circumvention. So the first one is that it's a problem that is affecting many millions of users on a daily basis. And this is a map that shows these are annual reports provided by the Internet Freedom House. And you can see this shows the map of internet freedom. I believe this is 2024. So the purple areas are regions with excessive internet censorship. Yellow areas are regions with half censorship, but not quite. And green areas are areas with not too much censorship. And as you can see from this picture, the problem of censorship is not just limited to 1 or 2 countries that we keep hearing in the news. It's a global problem, and millions of users deal with censorship on a daily basis. This is impacting their lives, this is impacting their access to information, democracy, human rights, and such and such. So the second reason that I like and enjoy working on this topic is that, in fact, it's also a challenging problem. It's a hard problem. People have been working on the topic of internet censorship, and censorship has been around pretty much since the beginning of internet. And a lot of smart researchers and students and developers have been working to fix this problem, but still we're talking about censorship and how to do this work, right? So it's a challenging problem. There's a lot of interesting technical challenges in performing research on internet censorship. And the final reason I kind of enjoy working on the topic is that it's also an interdisciplinary topic. It lies at the intersection of networking and also security and privacy and public policy, economics, law, and such. So you will find a lot of interesting interdisciplinary research problems on the topic of internet censorship. And there are different flavors of censorship. So maybe perhaps when I tell you censorship, the first thing you will come to your mind would be like someone deleting your post on X or TikTok. But this is the particular type of censorship that is the focus of my talk today, and it's network level internet censorship. And let me tell you what I mean by that. So suppose this is you, and let's say you're as old as me, so you like visiting Facebook. So when you go to Facebook, this is what you get. But let's say now you go to the next Impact conference or workshop, and it appears at this other country called Censoristan, just a made-up name for a country. And now you can try to get to Facebook, and instead you will get a page that looks nothing like Facebook. It's kind of shouting at you some angry message that you're not supposed to read, go to this website. And also sometimes it could happen that your connection just times out. You just keep waiting and waiting and nothing happens and you just move on. And this is the kind of network level internet censorship that is the focus of this talk. And in fact, this is the mechanism that is used to block many of the popular internet services, from different apps to different streaming media to social networking and such. Okay, so with that kind of introduction, here's kind of the three key parts of my talk. I will start with giving you kind of a high-level introduction on internet censorship and how it works. Then I'll talk about the recent case study of censorship, and that my colleagues and I looked at that case study. And finally, I'll talk to you about some of the lessons and challenges that I see on the topic of internet censorship. Okay, so let's move on to the first part of my talk, which is an introduction on censorship. So again, suppose this is you're in this country, Censoristan, and you want to go to Facebook. Let's see how the censors can actually block your connection. So internet communications are end-to-end, and anything that you do on the internet has an IP address or an identity, right? And therefore, the most trivial way of blocking Facebook is to learn what is the IP address of Facebook and add it to a block list, and that block list contains IP addresses of all the other websites and services that they want to block. And this is kind of one of the most basic mechanisms of censorship, which is referred to as IP address blocking. Now, when we want to go to Facebook, we don't memorize its IP address, right? So like we type facebook.com, and it somehow magically translates that facebook.com to its IP address. And this is done by a service called DNS. And therefore, the second basic form of censorship provided to the censors is when the user asks for the IP address of Facebook, they will intercept the connection and they will send a fake response to the user. Therefore, this DNS interference or DNS poisoning, and it has different names, this is the second most classic form of censorship. Now, I'm pretty sure you've heard of proxies and VPNs. And proxies and VPNs have been designed in part to help with bypassing IP address blocking and DNS interference. And the idea is that now instead of you directly going to Facebook or asking for the IP address of Facebook, what you'll do is that you will use a computer outside Censoristan, and you will connect to that computer, and your connection is encrypted, so nothing can be seen from your traffic. And then from that proxy, from that stepping stone, you connect to facebook.com or you go to that DNS server to ask for the IP address of Facebook. So proxying is also as old as perhaps the internet, and it's kind of the key idea behind most of the existing censorship circumvention tools. So a lot of the proxies and VPN technology, which is designed for censorship circumvention, it relies on this simple idea of using proxies. Sadly, this is not enough. Modern and state-of-the-art sensors are equipped with this capability, which is called deep packet inspection. And deep packet inspection allows the sensor to go just beyond the IP address and things like that, and look inside the packet, deep inside the packets, and look for detailed clues to be able to find connections that are established through the proxies. So deep packet inspection, it's kind of an umbrella term which is used for middle boxes or firewalling capabilities that can do a lot of different things. These include looking for packet characteristics like timing and sizes of packets, look for headers and try to identify signatures of traffic that might imply this is a proxy. Also sending probes to servers, try to see how they react, and based on that, those decide whether this should be blocked or not. But then regardless, this is a very powerful capability provided to the sensors. And I want to say defeating deep packet inspection has been pretty much the biggest headache to the circumvention community. And this is what the community has been trying to defeat, I want to say, in the past decade or so. And so when it comes to defeating DPI circumvention, I want to oversimplify the work so far into 3 major lines of work. Early on, there were these systems, they were called parrots, and their idea was, let's say Skype is popular and China will not block Skype because a lot of Chinese users use Skype, so we're gonna make Tor traffic look like Skype, right? That's why they're called parrots, because their goal was to kind of imitate some other protocol. And by the way, Skype is going out of business, so it's regardless, right? So this line of work then was debunked by this paper that we had over a decade ago, almost a decade ago, which says the parrot is dead. And the kind of key idea this paper demonstrated was that if you want to be a parrot, that's a pretty difficult thing to do, because the sensors only need to find one single discrepancy to be able to find whatever your traffic, to distinguish your traffic from the one that you're trying to imitate. But if you want to imitate as a circumvention system, that's a lot of complexities that you need to handle. So followed by this work, there was another line of work, I want to call them tunnels. And their idea was like, yeah, maybe looking like Skype is good, but then also imitating is not quite strong. So let's try to tunnel traffic through Skype. Right? So it's not like imitating and trying to look like a Skype. This is making an actual Skype call and tunneling Tor traffic through that actual Skype call. Right? So I can think of it like using some virtual modems on your phone, on your computer, that converts Tor packets into audio and then sends audio to the Skype client software. Right? So it's just the Skype underneath. Right? It's no imitation or anything like that. But then also, soon people realized this approach has different technical and legal issues. For one, if you're tunneling through a Skype, probably Skype is not happy about it, and if a lot of Chinese users do it, it's probably not good. At some point, they will start detecting and blocking. But also, like Skype or whatever protocol you're using to tunnel, it probably doesn't have the capacity you need for tunneling a reliable, interactive traffic like Tor, right? So then at some point, people also kind of stopped working on tunneling protocols. Now, I want to say the third stream of work on trying to defeat DPI circumvention is this kind that tries to look like nothing. They're like, okay, maybe the sensors have a way of identifying Tor and shadow socks and Siphon, and these are different proxies. So let's make our traffic in a way that looks like nothing and none of them, right? And if it looks like nothing, they'll probably just let it go because on the internet, there's a long tail of unknown traffic, right? I want to call this look like nothing systems. And I want to say this kind of idea has been used in a lot of the systems that we use today for censorship circumvention. So moving forward, I'll talk about the systems that, in fact, are relying on this idea of trying to look like nothing. So one of the key ideas that these look like nothing proxies use is to fully encrypt their packets. So network packets, even TLS, they have some unencrypted, non-encrypted headers, and those have been used by the sensors or other firewalls to fingerprint traffic. So these tools say, let's encrypt the whole damn thing, right? There's nothing unencrypted in the packet. And then with that idea, hopefully the sensors will not be able to get any signatures out of it because it's just fully encrypted, right? Unfortunately, this is an idea that proved to be wrong. And now I'm going to talk about a case study that the sensors actually showed they're capable of detecting proxies even if they fully encrypt the whole packet. Okay, so this is the second part of my talk. I'm going to talk about this case study. Here's kind of a short timeline of this event. So in November 21, a lot of users, proxy users in China, woke up to their beloved proxies not working, none of them. And interestingly, this was right before a major political event in China. In a couple days, our team members are able to investigate this new blocking and identify that this is in fact a new thing, and this is not like anything we've seen before. It's a new form of blocking. And then by early January, probably less than 2 months, our team of collaborators have developed some fixes for this new blocking, and our fixes have been adopted by major circumvention tools, and therefore unblocking a lot of users. So this study was published at Usenet Security 23 and received 3 awards, including this first place at CISA competition and Applied Networking Research Prize. Yeah, so the following slides, some of them I'm borrowing from Jackson. I hope he doesn't mind. Is there a question? Right, it just, so yeah, so the IP address, I'm only talking about the DPI. Yeah. That's right. So yeah, that's true, but that's a parallel problem. So you can solve signature censorship from IP blocking. So there are different kind of techniques to help with getting around IP blocking, like using a cloud kind of instance, right? But then, so whatever I'm telling you, it's assuming that the IP is safe, right? And in fact, a lot of these proxies that we'll talk about, they're run by users in cloud services, and therefore IP blocking is pretty difficult for them. Okay, yeah, but good question. We're just talking about blocking based on signatures and the traffic itself, but not IPs. Okay, so let me talk about this incident. So in the censorship circumvention community, the kind of basic tool that we have to study and investigate new blockings is internet measurements. So basically, we set up some vantage points across the internet, some inside the sensors region, some outside. And we start fabricating particular network packets that we send both ways. And of course, this needs to be done strategically so that we can understand the nature of blocking and kind of get clues into what's happening and how it can be prevented. So I'm not going to talk about the details of how we did internet measurement. In fact, this is pretty important, how you do the measurement. But let me just talk about what we found through the measurements. So what we find here is that we see that perhaps for the first time, the sensors are using an allow list for performing their censorship. So typically what they do is that they have a block list of things, block list of signatures or IP addresses and such. And in fact, this is why people thought, okay, let's do look like nothing, because if we don't look like anything, then perhaps we can get through, right? But then now the sensors, this is the first time they have come up with an allow listing mechanism such that they say, we're going to let through all the traffic that we know and we're sure it's not circumvention, and then everything else, screw it. We're going to block everything else, right? So we discovered that they're using this allow listing mechanism, and I'm not going to talk about all of these allow rules or exemption rules, but I'm just going to talk about two of them. So one of them, exemption number 1, what it's doing is that it says if the traffic is too random, it's probably a proxy. So remember I said these look like nothing proxies, they said let's encrypt the whole damn packet so that it looks like nothing, right? But it turns out that makes it too random. No normal traffic is that random, right? Anything that uses encryption, it has some headers and things like that that makes it not truly random. And therefore, it seems like the sensors did this smart thing that they came up with a rule of like counting the number of ones and zeros in a packet. And by the way, this is only done on the first packet of every connection. And then this rule says, if it's too random, it's a proxy. If it's not, we'll let it through. And then the 5th exemption rule, it's also pretty interesting. So a lot of the traffic that uses encryption belongs to things that run on HTTP or TLS. So this exemption rule says, we're going to look for signatures of TLS and HTTP, and if it matches, we'll let it through. And that constitutes a large fraction of traffic. Okay? So let me share with you some of the interesting kind of observations we made through the analysis. So the first one is that we see that the sensors perform this blocking only roughly on 1/4 of the traffic and connections. So even if you're sending traffic to your proxy, on average, only 1 out of 4 packets will get dropped or blocked, and the other 3 will go through. So what is the reason? Why do they not block the whole, like all the packets? This is kind of a common practice by the sensors, and they have different reasons. First of all, any blocking mechanism has some false positives, and this is what is known in the community as collateral damage. So the sensors want to block people who go to proxies and through proxies to Facebook, but they don't want to block like gamers and like video streamers and such, right? And therefore, by doing this probabilistic blocking, they're also trying to reduce those potential false positive blockings. The second reason is that any blocking also comes with a cost because you're running things on your routers, right? And therefore, by doing this probabilistic, they're also going to reduce the cost. And finally, this is enough, right? I mean, even if you drop 1 out of 4 packets, because I, like as a shadow socks users, I see that my connection is not reliable, that's enough for me to stop using shadow socks, right? So you don't need to block all the packets. As long as you make enough intimidation to the users, that would be enough to effectively scare them away from using those services. So the other interesting, I think, analysis I'd like to share with you is that the blocking is only implemented on traffic going through certain autonomous systems. And these are autonomous systems that are heavily used to host these proxying technologies. So a lot of these proxies like shadow socks and V2Ray and things like that, they're run inside cloud instances. And therefore, again, also to further reduce potential false positives, if the traffic is going to a residential ISP, or if it's going to a, I don't know, maybe university ISP that they're not likely to run shadow socks, they're not going to block it. Okay, so these exemption rules that we obtained, and of course it's based on doing a lot of poking and fuzzing and analysis, but how do we know that this is actually covering everything? Like, how do we know there's no exemption number 6 that we didn't identify? We really have no way to say that because this is just an empirical measurement. But what we can tell is that we can actually measure false positives, and this is what we did. So we ran the exemption rules that we identified on a large university network, and we see that only 0.6% of the traffic is not exempted by these rules. And that would be the upper bound on the false positives, because it's likely maybe someone also in that university was using shadow socks, but potentially not, because this was a US-based university, right? But at least we know that the upper bound on the false positive is likely pretty low. Okay, and we had, interestingly, no false positive, meaning that these 5 exemption rules were able to identify all the kind of shadow socks and proxy traffics that we sent through this kind of simulated GFW. Okay, so then how do we defeat or how do we circumvent this new blocking? It's probably straightforward at this point, right? So we know the exemption rules that the sensors are using, and therefore we try to make our traffic to match at least one of those exemption rules. So for example, I told you one of these exemption rules was about matching and looking for signatures of TLS and HTTP. So one of our circumvention mechanisms was to append a signature of HTTP or TLS at the beginning of shadow socks connections. And the other countermeasure we developed was based on, in fact, reducing the entropy of packets, right? Just adding a little bit of characters to the traffic. So, so perhaps this is a slide that my colleagues and I are most proud about, which is our circumventions were adopted by major circumvention providers. They get developed and adopted, and they helped millions of users by regaining their access to the internet. Okay, so so this blocking ceased to continue on after about a year and so. And interestingly, this was also right after another major political event. Okay, so with that, let me talk through some of the lessons and also challenges that I want to talk about on the topic of censorship circumvention. Okay, so let me start with the first lesson. So if you want to have successful censorship circumvention, you really need to understand the mindset of the censors. So the reason I gave you those timelines is that now I want to show you the bigger picture of the timelines. So this shows the timelines of blocking of 2 censorship events. The yellow boxes are censorship events, and the blue ones are some major political event in China. And you can see that almost always, whenever something new happens by the censors, it's very close to a major political event in China. So I guess what I'm walking away with this is that the censors time their actions. And this is, I want to say, is for 2 main reasons. The first one is that they want to strategize their censorship mechanisms. So remember, when they develop these censorship mechanisms, they also know that these will be circumvented at some point. So they save their mechanisms for the best time, for the time that they take the most out of their blocking, right? And right at the time that they need connections to be disrupted, they roll out that new form of blocking, and they know themselves that it will be circumvented after some time, but by the time it's circumvented, they've done the damage. And also during those political times, they can also tolerate higher collateral damage, right? Because now they can tolerate some gamers to be pissed off because it's really important for them to block the connections at that time. And I want to say the second reason that the sensors time their actions is that the censorship apparatus is formed of humans. There's a lot of bureaucracy in developing these censorship mechanisms and also in making decisions about whether these are safe to roll out and whether they're ready to roll out. So every time they develop a new mechanism, it needs to go through some certification or approval process, and that will take time, right? And that what this tells us is that even if they are ready to roll out a new thing, it needs to be approved, and that might take some time. Okay, but why is this important? It's important because we, as a circumvention community, we can actually take advantage of this kind of a slow reaction of the sensors. I mean, first of all, one thing we have to do is to think ahead of time. We should think about what the sensors could do so that we proactively develop countermeasures and we're ready for them to do that thing, and also we're ready. So the second thing that we can take advantage of is that stopgap solutions or short-term solutions that we know are easy to be also blocked by the sensors are still valuable, because even if your countermeasure is adding a simple header at the beginning of a packet, and even if the sensors know how to kind of block this new mechanism, it's going to take them some time before they can actually roll out their new blocking for this new stopgap solution. So perhaps censorship circumvention is one of the few areas in computer science that imperfect solutions or not bulletproof solutions are still good enough, right? Especially in security, like every time you write a security paper, they want to make sure that no attack, no adaptive attack, or no whatever attack works against your solution. But maybe this is one of the few areas that even imperfect solutions, as long as they work, they are still valuable. And also, I guess the other thing I want to say is that we need to be fast in learning about and identifying new blockings. So the second lesson I want to kind of share with you is that we need to embrace technology shifts on how the internet works. So I want to start with kind of mentioning this success story example, domain fronting. So domain fronting is this capability in cloud servers that basically allows to share IP address between different cloud instances. And when this was kind of provided years ago, it was seen as an interesting thing by the circumvention community. So a lot of proxies, Tor, and many other of those kinds started to run their proxies behind a domain-fronted server, and that worked pretty well. It was expensive, but it worked fine, especially if you wanted to use it just for the signaling mechanism. Sadly, cloud providers one by one started to disable the use of domain fronting for circumvention or at all. And I guess that's logical, right? I mean, they don't want to have circumvention traffic interfering with other services, right? But I think the lesson we learn from here is that even though domain fronting was good for some time, maybe that was enough, right? I mean, it served its duty, it's gone, but now we should be on the lookout for new opportunities. And in fact, there are new opportunities. I want to say, for example, one new development is the adoption of ECH, which also, similar to domain fronting, is able to hide the true domain that the traffic is going to. And also another possibility I want to mention is the QUIC protocol. It's in fact, it's getting pretty popular. It runs TLS inside UDP, so it has a lot of good capabilities for censorship circumvention. And in fact, some proxy services have already started to use QUIC for bypassing the censors. So I couldn't talk about impact, right? It's an impact workshop, so I needed to have a slide on impact. So this is probably a trivial lesson, but again, I wanted to have something on impact. So I guess in my experience, every time someone has made a big impact in this field, it's only been when they have worked closely with users and also actual developers, right? So I guess all the instances of research papers that have made a huge impact, you will see that they've engaged with the users, they've, through getting feedback, and also they've worked closely with developers to roll out what they found, right? So again, this is probably not surprising, but I want to say this is very important. Okay, now let me move on and talk about some of the challenges that I see on working in censorship circumvention. So the first one is that I want to say time is not on our side. And what do I mean by that? So I have another timeline. So this is the timeline of how we have fixed two censorship events. So the two rows, each of them represent two different censorship incidents. So as you can see, starting from the left side, you can see when that blocking first was identified, was deployed. So it takes some time for the community to detect there's a new censorship, and then it takes some time for the community to develop countermeasures or find fixes for that new blocking. And then even after that, it takes even a longer time for that thing that you found to be adopted and integrated into proxy services. And now you can see that for these two instances, these are both very long times, right? And again, by that time, the damage has been done, right? So I want to say that circumvention community is mostly, I guess some people may disagree, but I want to say mostly reactive to the censors. And what I mean by that is that we wait and wait until something happens, some new blocking appears on the internet, and then only after that we struggle to find a solution and to fix it, right? So I believe that we should change gears and we need to become more proactive. We need to be able to speculate about what the censors could potentially do in the future so that we prepare and we proactively develop countermeasures. But that kind of proactive approach is not that trivial. I mean, first of all, like I said, the main tool that we use, or the community uses, is internet measurement. And measurement can only measure things that exist. With measurement, you can only measure the existing forms of censorship, right? But what about if you have a new version of ShadowSox and you haven't even rolled it out? How do you know how it might get blocked, right? So therefore, I want to say that to be able to do proactive circumvention research, we need to build new playgrounds for censorship research. We need to build emulation environments that allow us to just run arbitrary protocols and arbitrary censorship mechanisms and circumvention mechanisms and play with them. Like, let's say even if you're an app developer and you want to roll out your app, before doing that, perhaps you can run it inside that censorship emulator and see what are the possibilities of it getting blocked and how, right? I want to say we don't have those playgrounds, and I think that's what the community needs to work on. And also, there's a lot of value in doing empirical research in censorship, and a lot of good things have come out of it. But also, we need to couple it with more rigorous theoretical analysis. I mean, there's been some work trying to use game theory or reinforcement learning or information theory and things like that, but they've mostly been at kind of on toy problems and just to demonstrate the possibility. And I believe that a lot can be accomplished by kind of adding theoretical analysis, or I guess complementing empirical research on circumvention with theoretical analysis and assessment. Okay, so the second challenge is about the unique ethical and legal dilemmas that we have in this field. So if you think about it, when you do censorship circumvention, you're breaking the law. Perhaps not the US laws, but someone else's laws, right? And therefore, if you're not careful, it's possible that you cross some fine kind of ethical and legal boundaries. So let me ask you some questions. So I think, in fact, the first question is, are we allowed to develop tools to help censored users? I think most users would say yes to this question, right? At least my sense is from the community. A lot of people will say yes, because censors are weakening internet freedom, and in fact, a lot of even funding agencies in the US are supporting funding for this kind of work. Okay, so this seems like believed to be ethical and also legal. But what if I ask you, can we cyber attack the censorship system? Can we send denial of service to the Great Firewall of China, for example? And I'm pretty sure most people will say no, right? I mean, first of all, this has a lot of, maybe you will say yes, but I said most people, yeah. But I mean, first of all, there's a lot of, at least no one will fund you, will give you funding to this kind of research. I mean, first of all, there's the potential for ramification by the censors. And also, because it's their network infrastructure, by doing so, you might also hurt some users because you're breaking their systems, right? So you might also do other damage, right? So this seems also, at least to a lot of people, a clear no. But there are also a lot of gray area questions that people debate, and there's a lot of disagreement. So like, for example, what if I tell you there's a vulnerability in the Great Firewall of China, and you can use it to learn about how their system works? Would you use it, or do you have to disclose it because it's a vulnerability, like the responsible disclosure, like we researchers in security? That's the thing we do, right? And also at some point, like if you decide to do responsible disclosure because of a potential harm, how long should you wait before doing it, right? I think the other kind of gray area question is, should we let censored users to do whatever they want with our tools, right? So yes, we give them a pipe to tunnel traffic, and they could also do illegal things. They could also do harmful things, right? So then should we even allow systems like, I don't know, proxies to be just a blanket proxy for everything? So with that, I don't want to talk about like these questions, but I want to perhaps encourage you to take a look at this paper that was presented also by Jackson this week, earlier this week at NDSS. So we find a vulnerability in the Great Firewall of China that if you send a malformed DNS query, it actually dumps some of the traffic it's intercepted. So I guess if you would like to, I guess, think about some challenging ethical questions, I encourage you to read this paper. And this is one of the papers with a box on the top, right? And you always know something's wrong. But I mean, of course, we stand by the research, but anyway, I think this would be a, I guess, interesting read if you guys get a chance. Okay, so I want to say the third challenge is about the unique human safety risks that exist in the field of censorship circumvention research. I mean, first of all, when you develop your research methodology and your measurement techniques, you need to make sure it's not harming typical users. So let's say you send a traffic which contains a forbidden keyword to a Chinese user, and then that Chinese user then the next day is knocked on the door by the officials because they think they send the traffic, right? So therefore, in developing your research methodology, you need to take extreme care into designing safe measurement techniques. Now, the other aspect of safety risk, which is in fact often ignored, is the safety risk to the researchers and volunteers. Unfortunately, the people who run the research at dire risk from the censors. I mean, there's the risk of being detained when they travel to those regions. There has been instances of cyber attacks by the censors against the researchers' infrastructure and personal devices. There's been cases of family intimidation. In fact, a lot of people who do research on censorship circumvention come from regions with a lot of censorship because it makes sense for them to work on those topics. And therefore, it's likely they have family back there. So therefore, there's a lot of also risks to the families of people who are involved in disclosing censorship and finding solutions. So therefore, we need to, I guess, talk about in the community how to better protect our peers. I think I want to say one of the things that is essential is allowing people to publish anonymously when they do sensitive topics like censorship. It used to be that people could do anonymous publications. It seems like more recently there's new hurdles in being anonymous. I don't want to name, but some major publishers in our community is now not allowing anonymous kind of authors, which is making it impossible for people to publish. I think, again, I don't want to talk about the details, but I mean, unfortunately, this is something that, at least I know, is scaring some researchers away from continuing to work on this topic. And I guess we also need a lot of human research on the safety and also on the social aspects of performing this kind of research. So the last challenge I want to talk about is, as you probably have guessed, censorship and AI, right? I'll talk about LLMs. So first of all, we know that large language models and AI in general has revolutionized all the fields that we know, right? Everything is starting to change or has already changed. And there's a growing evidence that the censors will also start heavily using LLMs and AI for enhancing their censorship. So I guess the first thing we need to do is we first need to fully understand the full capabilities of AI and large language models in assisting the censors. We don't even know that yet. We don't even know the power of LLM that can be provided to the censors. And also, we need to also be able to detect when AI is used by the censors, right? I mean, like the nature of censorship, it's passive, and it's really difficult to know what is being used and when it's being used. So I feel like these are challenges moving forward to understand when AI is being used and also to understand what AI can do. Now, the flip side of this problem is not AI for censorship, but censorship in AI. So again, AI is getting integrated with all the tools that we're using. And therefore, if I'm a nation state and if I want to disseminate my propaganda, the best way is to package it into the LLMs that I'm shipping around, right? And then once this LLM, if it has some kind of misinformation or disinformation encoded in it, when it's used in some apps, that is also translated to those apps. So I want to end with these kind of examples that we have been playing with DeepSeek. So if you ask DeepSeek about domain fronting in Signal, this is what it tells you. It's kind of a boilerplate template response, right? It just tells you that internet governance, policies, blah, blah, right? It seems like it knows it's a sensitive topic that it's not supposed to respond to you, and it has a template response. So with DeepSeek, it's a reasoning LLM, so you can actually also see the reasoning, that you can actually see the chain of thought. And when you look at the chain of thought, you actually said it doesn't even think, right? The chain of thought is empty. It just looks for the keywords, and right away, it gives you the template boilerplate response. And this is kind of another example that when you ask it about a political topic, sensitive topic, it gives you another boilerplate response. And it's, as you can see by the topic, it actually changes the template response they have. And this is not something that they're hiding. In fact, when you ask DeepSeek, it will tell you that I'm designed to censor, I'm designed to abide by the rules of the Chinese government, right? So therefore, I see this as a big challenge, not just to censorship, but also in general to flow of information and propaganda and things like that. So with that, I'd like to conclude, but I want to say the credit to all the for all the work that I mentioned, and also all the work in the community goes to the brave students and researchers and developers. They gamble with their peace of mind and safety and even careers. And I hope we all can provide a better support for the students and researchers who work on these topics. Thank you so much, and I'm happy to take questions.
Hi,
Hey.
very nice talk. I'm wondering if you've had any interaction with standards bodies, like internet standards bodies, or if you think that there would be a potential for interaction with internet standards bodies to consider censorship circumvention, preventing censorship, as a goal of protocol design, a goal of system design. I recall that like, post-Snowden, I think it was IETF, like put on an RFC that said internet surveillance is an attack on the system, and so we should design our protocols to resist internet surveillance, basically saying we need encryption everywhere. You could do a similar thing and say censorship is an attack on the network. We need to have protocols that have no metadata that's unencrypted. We need to have secure DNS lookups so they can't be blocked or they can't be modified. We need to have secure transport protocols so that resets can't be inserted artificially. So yeah, I'm wondering if you think that if you have had interactions with these standards bodies, or you think there's a potential for them to contribute in the longer term, of course, not next year, but maybe in 5 years, towards making this more difficult from the censorship perspective.
Yeah, thanks, Aaron. Yeah, I think that's a great point. So I haven't had too much interactions myself. I know there's some support for it, but also I know there's some pushback because these standards will not be just deployed in the US and Europe, but also in those countries, right? And therefore, there's a risk that if we make something a standard that kind of makes censorship really hard for the censors, it's likely they would allow the adoption of those protocols, right? So I think, I know there's been some battle and some push in the community to push for standards that help internet freedom. I think one thing that has helped is to look for two-purpose, like dual goals for these things. So like, let's say if I say DNS, like encrypting DNS helps to circumvent censorship, but also helps with security in general, or maybe if it can help to prevent from some kind of phishing attack or whatever, right? So if you come up with a second goal that is more aligned with security and enhancing privacy and those things, I think that that's an easier case to pursue. But I feel like just censorship, I would expect there would be not too much support in making those into standards.
Well, let me ask about a specific example of this, which would be the encrypted client hello. I don't actually know the current status of this, like if this is part of the standard or not, but I thought that China was blocking TLS 1.3 with encrypted client hello.
Exactly.
So if that is the plan for going forward for TLS, that we're going to have encrypted client hello, I don't know if it is, you could answer and tell if you understand, then do you see this already happening where China has one TLS and the rest of the world has another TLS?
Yeah, I guess it could be, yeah. So I think it could also fraction, like, I think the other risk is that if I'm like a major app developer and I see that like this version of TLS is blocked in China, I might even refrain from using it, right? So that's the risk, that even if you make it a standard, like app developers might just stick to things that are not blocked in China, right? Like you said, there's been blocking of ECH or ESNI and those things, right? And if it happens, if it's deployed by the sensors, even if it becomes a standard, it won't help that much.
Thanks.
Sure.
Other questions? Then I will go ahead with a question. You mentioned about theoretical research on censorship circumvention. So if I have to ask you, like, what would be the next, or what would be the result, or what kind of research would you like to see, or what do you think would help in the next 2-3 years?
In censorship circumvention, so like I said, one of the things I like to see is a kind of some playgrounds to allow us speculate about censor actions. So things that you could, again, playgrounds that you just run protocols. It's easy to use by average developers, right? And you run your protocol and you have like a drop-down menu of censorship strategies and sensors and whatever. It's like a user interface. You pick different settings and then it will tell you that this protocol in this setting will potentially face these blockings, right? And such a playground can also be augmented with, like I said, analytical tools, maybe things like reinforcement learning or game theoretic analysis and things like that, right? So I think those kind of platforms, so again, currently we're mostly relying on internet measurement. First of all, it only sees what exists. Second, it's expensive because you need to pay for a lot of vantage points and things like that. And third, there's a lot of safety risks to doing internet measurement. But having playgrounds, again, as something that will complement internet measurement, I feel like that would be a big thing moving forward for the circumvention community.
Okay, just quick question. On your first map, there was something painted black.
Black?
Do you remember what it is?
It was probably regions that
Irrelevant.
they didn't have data.
Okay,
I guess.
makes sense. Okay.
Yeah. This one, right? Yeah. I think those are regions they didn't have enough data to make a determination.
So most of the work that we see in anti-censorship is focusing on China for obvious reasons. And I'm wondering, like you show in this map, like other countries, especially let's say like, I'm from Tunisia, for example, that they're not very powerful countries, technically. They also have some form of censorship. Do you know if they get it like imported, the technology, or they develop it themselves? And if they do, like, are they usually easily circumvented? Like we just don't know, right? Like we have the only thing that we measure, we know that there is censorship, but to my knowledge, I don't know, for example, how Tunisian government would like censor these things.
I think that's a great question. I mean, increasingly you see papers that look at new countries. I think we have few papers that look at different countries. So, I mean, some of these, there seems to be evidence that they're purchasing their techniques also from the big guys. But also we can see differences in how these censorship techniques work. But many times the tools that people develop based on the study of China has also helped other countries. So like, for example, the thing that I mentioned, the case study that I presented on Great Firewall, that coincidentally overlapped with the Mahsa Amini movement in Iran. And the same tool that we developed for China, it actually helped users in Iran. So it seemed like they also had somehow acquired the same mechanisms for blocking. I don't think we have any evidence, yeah. By obfuscation, that's possible, yeah. But I mean, it's also possible that they kind of transfer technology between themselves, right? I wouldn't be surprised if they just have a contract to exchange technology, yeah.
Other questions?
Thanks for the amazing talk. Maybe a slightly different question. Do you feel there will anytime, be a time that we can move away from the cat and mouse game that we have in censorship circumvention in general, on the positive or on the negative side, that, it's like either you can, access everything, or it's like we are moving towards a zone where it's like probably you'll not be able to access anything in the long term, at least on some part of the world.
Yeah, that's an interesting question. Yeah, I feel like, I mean, we probably can't solve the problem for good because the internet is not designed to be resistant to censorship, right? It wasn't one of the core features in the design of internet, right? So we're like patching it, right and left, and we'll probably continue doing it. So, and also on the other hand, I don't think the censors will, I mean, of course, one side of the game is that if the censors disconnect themselves from the internet, right? And in that case, I mean, of course, there's no cat and mouse game anymore, right? But there's a lot of economical reasons most censors won't go that way, right? I feel like the way the internet is evolving will tell us which way it will sway. But I'm hoping that at least we will continue this as a cat and mouse game, right? And I mean, doing a cat and mouse game, it's actually not too bad as long as we shrink the response time in the community. If the cat and mouse game is always them doing something and we reacting to it in 2 months, that's not a good thing. But even if it's a cat and mouse game and we are all the time, like maybe in a week or something, we develop the solutions, I don't think that would be a bad thing.
To resist censorship, because we also say
Or to
that
have
in
security.
privacy. Or privacy as well, because especially
Exactly.
metadata privacy. And
Yeah.
I know a few years back, European Commission have funded like a small project to can we create the internet from scratch? And
Yeah.
everywhere, all the professors, they thought this is ridiculous.
Yeah.
But some people like worked on it, especially
Yeah.
in the open source community. Do you think like at some point we will have to like actually stop and like maybe redesign the internet?
I mean, I highly doubt it. I mean, in fact, there's been a lot of efforts, like you said, on redesigning internet, things like NDN and Mobility First and Nebula, all the names, like so many names that people came up with these new architectures. I think the problem is with the adoption. Like, who would adopt this new internet? Because they have to throw away all of the routers, likely, because this is going to be a new thing, right? And there's going to be some disruption in connectivity because, right, I mean, like, not all ISPs can switch at the same time, right? So I feel like this there's a huge adoption problem that I don't see, like totally switching to a new internet architecture. But gradual changes are possible. In fact, things like CDNs came out of these efforts into redesigning the internet. Like CDN came out of these internet-centric networking paradigms, right?
Thank you so much.
Sure, yeah.
I have worked on some of those alternative internet architectures, and unfortunately, they don't go any far. But the question is different. Is there any hope with low orbit satellites, or these are irrelevant for this question?
You should ask Musk. Yeah, I don't know. I mean, this is technology. I mean, it's kind of a paradigm shift, I want to say, in a sense that you're switching control to some other authority, right? So, like, for example, we've just, I think, reading in the news that Musk had, I think, said something about disconnecting Ukraine from the satellites, right? So it seemed like a good solution, but now someone else is the big boss, right? But I mean, from a technical perspective, it's a good complement to the current internet, as long as there are multiple providers who can compete, both from the economical perspective, so the price is right, and also for kind of censorship kind of perspective, right? Also what? Jamming, exactly. Yeah, yeah. Jamming is also a problem. Yeah, it's I think, and in some countries, people have been jamming satellites for a long time. There's been a lot of health-related issues to jamming, like at a larger scale. But yeah, they're also prone to jamming. At least maybe during sensitive times, perhaps they could intensify the jamming, right?
Any other questions? You seem to have another question. Okay, good.
I do have one,
Sure.
Very interesting talk. Thank you so much.
Thank you.
So, in the DeepSeek example that you chose, is that how the LLMs are trained, or do you think they are filters? Because I tried the Facebook one, I did not try the DeepSeek, and certain questions gives you like what you expect on different topics, but similar. But then when you do it locally, and like I disconnected from the internet, and like I remove these filters, then it kind of like it's a statistic game, right? And then it'd be like, this is what actually the statistics are, blah, blah, blah. Do you think for DeepSeek is the same? Like it's actually tokens that they were training the data because...
Yes. So I think it's a strain because we actually did this on a local model, a downloaded model. Yes. It's not just the API interface. It's trained and fine-tuned to implement censorship.
So that's like really hard to fix. Unless like when you have filters, right?
Yes, I mean, I guess the biggest problem is to identify the blockings. Like, how do you kind of infer the list of blocks, block lists, right?
Yeah.
So that you go about fixing it.
Okay. Thank you so much.
Of course.
If there are no more questions, let's thank the speaker again.
Thank you
Thanks
so
a
much.
lot for talking here.
Thank you.